Okay, so I would point out that you know I'm not on my computer every hour of the day. I do try to be available for answering questions, especially as assignment due dates come up, and um, and this means that I run. I have Piazza on my cell phone, and I do not have notifications turned on for email on my cell phone. I have approximately 142,000 unread messages, and more are coming in, every minute. So, however, I do have notifications turned on Piazza. Um, and so far, classes haven't been sufficiently enthusiastic to make me regret that. So if you want to get a response to something, you're probably better off, off hours, you're probably better off sending to instructors. This also means that the TAs can see it. If you are asking about, submitting a homework late because of extenuating circumstances or something like that, particularly the short homeworks, the weekly ones, that is best done on Piazza, tagged to the particular homework, because that way, whichever TA ends up grading that homework can't see my email inbox, but they can see Piazza, and they can, quickly search for any posts that were tagged, homework 3 or something like that. And so, they'll see your query and my response. I'm pretty lenient if something came up saying, yes, you can turn it in a day late because you were sick all weekend or something like that. Finally, I would add that some of you will attach to, when you're doing the programming assignment, there's a few of you who've felt that you had to document something by attaching a full screenshot of, your entire screen. My phone isn't that big. I cannot read your screenshots when you post them. Not only that, but Piazza on the iPhone has a bug where when you try to view a screenshot, a lot of times it just gives you this blank window saying preview. So, at most I can use like the accessibility to zoom it in a couple of, 2 or 3x. So you probably want to include some, more information in your text so that I can understand what's going on, or else, a response is going to be delayed until someone can look at your post on a laptop and figure out what's going on. Okay. So I'm changing the homework late policy. The syllabus said that you can't submit the homework late, and we'll drop the lowest two. It seems unreasonable to change a drop policy too much midstream, so I'm going to say that for the first half of the class, we'll drop one, but then we have, if it's less than a day late, -1. If it's a couple minutes late, no big deal. If it's less than 2 days late, -2. And if you get it in before the TA grades the homeworks, which you don't know when that is, then you can still get 2 points for a successful answer. So that's about it. I did want to ask, now that you've done your first programming assignment for this class, how was the experience? How many people thought it was too easy? Okay. How many people thought it was too hard? And how many people spent more time on, or at least aggravation on, the sort of accidental parts? How many of you spent less time on actually doing the work for it and more time on getting your computer set up, getting, GitHub, doing all the random administrative crap that you have to do to get the assignment done? Okay, yes. It's, there's a significant part of, at least, practical computer science, if you're building systems and things like that, that is, how would I say, making computers behave. Doing stuff which is not theoretically interesting, exciting, or not always well documented, and which, in a perfect world, you would be able to use those neurons to remember something more valuable. But it's. I will say that I am regretting that I ever posted instructions for hooking up VS Code, because that has been a time sink that sent several of you down a path that where you spent a lot of time doing something that myself and the TAs aren't particularly good at, and and that's not what I'm trying to teach you to do. I'm mostly interested in the code that you're writing, the idea that you get familiar with being able to use the debugger, use the terminal, and otherwise, and you need to be able to use GitHub. I mean, this is 2025. If we are probably, for the next decade of your career, you're probably going to be pushing code to GitHub and dealing with merge conflicts because your colleague did something stupid, or worse yet, because you did something stupid, and otherwise, hating it. And it's a fact of life. It's better than some of the things I've had to use in the past, maybe worse than one or two of them, but it's what it is. So, I'm sorry if this is the class that had to force some of you to learn Git and GitHub. It could be worse. We could be doing team assignments, and you're and your lab mate could be causing merge conflicts every day. So, all right. Any questions about things that we could, that you would like to see, any suggestions on the next lab? We'll be sending that out tonight. Now that, it's late, it's been enough time that I can be sure everyone's Slack hours, or at least after we correct them, are, reflect when you turned in when you did your last commit. Is that a hand raised? A little louder? Okay. Yes. Okay. So yes, and actually this assignment was sort of, so yes, I'll talk a little bit more about C. This assignment was partly designed, oh yes. Okay. Yes. I will try to do a lecture. I will try to do a part of a lecture on testing strategies and testing in C. Now, one of the things is that, this is, the assignments we have in this class are not, pure functions that you can give a function some input and check the output and so on. In this case, for instance, everything is a side effect. You have this CPU state, you execute an instruction, and and then you verify that the state has been updated properly. That's a characteristic of systems, is that typically they're state-based. You have things that happen, and then you want to see that the right result occurred after it happened. So it involves designing tests based not just on the structure of your code, but the structure of the problem itself. In this case, it's fairly simple. You've got 15 instructions. Let's call it 7 and 6. 28 instructions if you count all the different, math operations and the different jump conditions. And, some of those have variants, so add another, it's probably about 35 or something when you take, register indirect versus absolute address, you take byte and word, and you have to take the logical problem, this CPU definition, and break it down into those cases, and for each case come up with a test that will that will verify that it's doing the right thing. For the purposes of this assignment, it's pretty much enough to verify that it did the right thing, and you don't have to go to great lengths to verify that it didn't do any wrong things. If you do the store instruction and it's supposed to write, you have 1, 2, 3, 4 in a register, and you write that to address hex 1000. If you verify that 1000 contains that address, then it's probably good. I think the grading test actually checks that, you didn't write anything to, the word before or the word after, some things like that. But, it's, here just checking that you did the right thing is probably enough, because you're probably aware that you didn't write additional code to do the wrong thing. So once you fix the code you wrote, it's doing the right thing. A couple of things. So the structure of the tests that you were given, which the sort of framework was, now, okay, the standard I/O library does okay. The system calls are significantly more expensive than functions, and if you're writing to a file, for instance, if you write 100 bytes, then another 20 bytes, and so on, that becomes very expensive because you're repeatedly updating the same file. So the library that we typically use will put stuff into a buffer, and then every once in a while it will write it out. Now, if you're writing to a terminal, it will look at the text that you're writing out, and whenever it sees a new line, it will be sure to flush the buffer and make sure that the data goes to the output. We'll see this in the next assignment, is a simple shell, and there you want to print a prompt and then no new line. You want to just print this out, and then when the user types something, it'll go on the same line. So in fact, we have to explicitly call another function the flush function to tell it that this is the do it now, damn it button. And there does appear to be, so there seems to be something which happens. I believe it was only happening when people were using the terminal in VS Code, where if you ran this test and you had a bunch of printfs in here, and then it crashed on the assert, sometimes those printfs got swallowed in the buffer and they never got printed out. Now, if you run it under the debugger, it's going to, you would see those, and it would also stop at the point where the assert failed, so you could actually poke around and see what happened. Now, how many of you ran the debugger on your code while you were doing this assignment? Okay, it's my goal to have everybody here use the debugger at least once during the course of this class. I guess one way to look at it is, many of you are asking for help from the TAs in getting your, in figuring out what's wrong with your code. I would expect that you would at least make an effort to debug your code before asking for help from the TAs. It doesn't seem reasonable to expect the TAs to put more effort into debugging your code than you do. They're here to help you, but not to do the work for you. So, we want to get everyone through to completing these, but, please, one of the things that we are trying to teach in this class is how to debug code. All right. So, any other questions on the programming assignment before I move on? This is sort of a very simple way of setting up tests. You just, you set up a precondition, you run your function being tested, and then you assert that various conditions are the case afterwards. We're not going to be using this for, that approach probably isn't that helpful for the second assignment. What's really most useful for the second assignment is writing a shell script and running it with your shell. Yes. Yes, I should be able to have them, by later this week. I just have to figure out, obviously everyone who got 30 out of 30 is going to get, the full 10. I just have to figure out the, and the people who didn't pass any tests are not going to do well. I still haven't quite figured out sort of, how to, well, I'll have to go case by case on the ones in the middle, because some tests honestly are worth more than others. If we got you on a narrow little corner condition, that's different from, your push instruction just doesn't work or something like that. But yeah, the grades will be out soon. Luckily, a large number of you got all the tests working. Thank you. That makes my life much easier. I just, do a grep for result 30 and put 10s in the spreadsheet for that, and I don't have to think about it. So in the previous lecture or lectures, I talked about address translation. And so how you have a hardware memory management unit that translates virtual addresses to physical addresses, in hardware by referring to a page table in memory. And it also has this TLB, which caches those translations so that our computers, run faster than my wristwatch or something. And the interesting thing, most of the interesting things that are done with virtual memory are not in that translation table. It's what happens if there's no entry in the page table, or if an access is prohibited. So okay, and basically, if you try to access, if the CPU makes an access to a location that's not present, that P bit in the page table entry is false, which is, sort of the equivalent of a null pointer in our normal software data structures. Or if it's marked read-only and we try to write to it, in both of those cases, we'll get a page fault. Now, a page fault is a little bit of a different type of exception, because normally let's say we're executing instructions. If we get, if we had a function call, that would actually be, a separate instruction in our instruction stream. If we get an interrupt from hardware, that happens without our code doing anything, but it happens between two instructions. So we execute one instruction, and then from our software's point of view, the CPU takes a vacation. Some, nanoseconds or microseconds later or whatever. In other words, our software is executing, and it just so happens that the time between when this instruction executes and this other one executes is a lot longer than normal because an interrupt happened. But page faults are different. A page fault retries, once the page fault handler returns, it retries the instruction that faulted. And this is what lets us do, this is really powerful. This means that, what if this address wasn't mapped in the physical page table? Well, in the page fault handler, the OS can go and do something about that. It can change the page table, and then when we retry the instruction, suddenly that address is there and it works. In other words, that page fault handler lets us fix things and then retry the instruction that faulted. And that's really powerful for a few reasons. In particular, let me get this out of the way. It puts software in the loop because all of this translation happens in hardware. It has to. It would never be fast enough if you were running code to do it. You know, it's happening on every instruction. Every instruction fetch is from a virtual address, and it has to go through memory translation. Every load or store is to a virtual address, and that address has to be translated. So in fact, every instruction, you know, involves, you know, at least one and often multiple memory accesses. And, you know, we can't run software on every one of those accesses to do translation. What we can do is we can leave an entry in the page table, you know, unmapped, and then when software accesses that, we can calculate what we want to do in software, and then we can, you know, patch up this address and this location in the page table and retry the instruction. You know, in a simple CPU like the one that we just implemented, just about every instruction can be easily retried. It turns out push and pop and call are a bit weird, but something like store, if it didn't work the first time, we can try it again, and it's going to have exactly the same effect each time. In more complex CPUs, well, it turns out the page fault has to save a bunch of information about internal processor state when it does a page fault, and then, you know, it loads that information back, and it actually returns to somewhere in the middle of the instruction. You know, that's we're not going to worry about that. There was at least one CPU in the past where they tried to do that and they didn't store all the information they needed to. That's why, like, the first Macintoshes didn't have virtual memory, because that CPU had a page fault mechanism and it was broken. So you know, I've mentioned before, the page table is this particular format. You know, to define the structure, you go and you look in the documentation that the hardware vendor provides, and the format of the entries in this table are, you know, the way they are because the transistors in the CPU that load that entry are wired a certain way. Now, an operating system like Linux, the operating system itself is going to have an internal view of what the memory structure of your process is supposed to be. And that is stored however the, you know, programmers writing that wanted to do it. You know, it's a piece of software that's keeping track of, you know, the OS view of your process address space, which is often somewhat different than the hardware view. So I forget, I think it's a struct mm in Linux for memory map, continuing the Unix tradition of inscrutable names for things that are hyper abbreviated. But it will be written in a way that's probably hyper optimized to be able to look things up in this page fault handler. And typically it's going to have so there's going to be a list of regions here. You're something like this, where here here's a memory map, and we have a very simple program that has one region for the code, one region for data, one region for the stack. And so somewhere in the OS, for that process, it will have a list of these regions and information about how they should be treated. And it uses that information for handling page faults. So every time it gets a page fault, it looks up the page fault handler gets the information it gets are basically, it gets the address, whether it was a read or a write, probably some other information, and we look up in this table to figure out what to do. Now, okay, the first thing we can do is, if that access was to here or here, to somewhere that's not defined in this table, then that's a bad pointer. You tried to dereference a null pointer, or a small integer, or a negative number that turned into a very large pointer. That's your mistake. There's nothing that the OS can do because you're trying to access memory that isn't defined by the program. So it crashes the program, basically. It exits the program. It's, in that case, the page fault handler never returns. Instead, it does, a variant of what the OS does for an exit, and reports back, a status code saying that it's been killed by a seg fault. If any of you got a report on Gradescope saying that a particular test had crashed in a segmentation fault, that's actually how we did it. We run each test in a sub shell, in a sub process, and then that test either reports its result back or it crashes, and if we detect the crash, we print out seg fault. Now, the rest, assuming that we find a region that's defined for the program, then there's a couple of, the action we take is dependent on the type of region we find. So the first type we'll discuss is demand allocate. And so if you use malloc to, allocate, 10 bytes, it goes and allocates, some memory that exists out of its pool. But if you ask it for, 10 megabytes, it's going to malloc will ask the OS for 10 megabytes, and the OS will lie to it. It will return a region of address space and say, I gave you 10 megabytes here. But in reality, none of those positions in the page table have been filled in. And then the first time you try to access a page in that region, you'll get a page fault. The OS will say, whoops, I told the program I was going to allocate a page here. So it allocates a page, it puts it in the page table and returns. So this is lazy allocation. Because of the page faulting mechanism, we're able to tell the program that we allocated memory, but we don't actually allocate it until they access it. And in most cases, this works out really well because, let's say, well, the stack is a good example. You can allocate a nice big stack for the process so that it's not going to run out of stack space, but most processes don't use a whole bunch of stack space. And so each time the stack goes deeper and accesses another page, will allocate a page and will return, and will only allocate enough pages for that part of the stack that actually got used. So this way we can allocate address space for the worst case, but we allocate real memory for what's actually needed. And it turns out there's a lot of cases, if you really need a gigabyte of memory and you're going to be using every byte in that range, yes, it will be quicker to, allocate all those pages at once and put them into the page table at once rather than taking a bunch of page faults as we do it. But the sort of code that needs to do that is rare. Most code, even if it does use that, all of the pages in that gigabyte eventually, is probably going to access it slowly. And rather than taking, even if it takes a little bit longer with all the page faults, which involve, a function call, they involve an exception. So it's, this page fault is more expensive than a simple function call. But if you're just handling the page fault, in memory by allocating a page, it's not that expensive. And, if your program needs this space but uses it gradually, you'll get a more responsive system if you fill in those pages as you go, as the program uses them, rather than taking a big pause at the beginning to set them all up. So, the OSs definitely depend on demand allocation to both only allocate as much memory as needed, because no matter how big the memory on our computers grows, we never have enough, and also to spread the work out instead of doing it all at once on startup. I'll make a comment about that as well. For most of my career, memory was getting cheaper by large amounts every year. And then about 15 years ago, that stopped. So, I don't know, if you bought memory for a gaming machine nowadays, it probably cost you about $4 a gigabyte. In 2011, you could go and buy RAM for $4 a gigabyte. So we're in a very weird period of computer evolution where at least one of the resources isn't getting cheaper every year. And so, as you're, at least in the first decade of your career, things may well be shaped by this essentially increasing RAM scarcity that it's something that certainly most of the computer scientists of my generation have no idea how to deal with, because we never dealt with that until, fairly recent years. And we didn't really notice it even until, 5 years ago. Okay. So another possibility is that a section can be demand load, which means where here the OS is lying when it said it allocated memory. Here we're telling the OS to read a file into memory, and it's lying about that. And then when we access a page, it says, oh, whoops, I promised I would read that page into memory, so here, not only do we allocate a page, but we read the contents of that page from a file. So in this case, we've got 7 pages here, because if you remember, the page size is 4K, 3 hex digits is 12 bits. So this is pages 0, 1, 2, 3, 4, 5, 6 in this range. And so I'm assuming that this file is 7 pages long, or maybe there's some additional information saying these 7 pages from somewhere in the middle of the file. And, and rather than actually allocating the pages in memory, the OS just writes an entry in this data structure saying that these addresses are demand loaded from this file. So again, for the demand, for both this and the demand allocate, when I say the OS is lying to the program, all that the OS does is it updates this little in-memory list of virtual memory regions. We allocate an address range for the stack. Well, it puts an entry in here. What does that entry do? Well, nothing until we get a page fault. And then when we get a page fault, it looks up the faulting address, says, oh, this is a demand allocate region. Let's allocate something. For demand load, we put a line in this table saying this range is demand loaded from this file. And then there's an additional step in the page fault handler saying not only do we have to allocate a page, but we have to read it in from the file. And the key thing in each of these cases is that your program is unable to detect that the OS did not, in fact, allocate that memory, or that the OS did not, in fact, read that file in when you asked it to. There may be, a microscopic delay when you access when you access a page in that range. Very difficult to measure in the case of demand allocate. Possibly longer if it's demand load off of a very slow file system. But in each case, the only way that you would be able to tell that a page fault even happened is if your code was collecting time. If every second or third instruction was collecting a fine-grained timestamp, and you started comparing how long it took between these instructions, because the fault happens and then returns back, and your code is unaware of the fact that that happened. Just like a hardware interrupt, it's this exception that's invisible to your program. Now, there's in In Linux and a bunch of Unix-like systems, they use an executable format called ELF, extensible linking, I don't know, it's ELF. And there's a header which defines various regions, which basically defines virtual memory address regions and then how to fill them. So, and most of that how to fill them is, oh, you take this section out of the file. You know, so code, you know, other things. There'll be another entry here for uninitialized global variables in C and other compiled languages. If you have a global variable that you don't set to anything, it's 0. It starts out as 0. It turns out the compiler gathers those all together into a single segment, and instead of including a whole bunch of zeros, there's another line in this header saying, oh, this address range is going to get filled with zeros. But we're not going to go into detail about this, but basically what the exec system call does is it replaces this data structure, this memory map in the OS for your process with a new memory map built from the header of your executable file. And then another field in this is what's the start address. It turns out it's not main, it's some library function that sets things up and then calls main. And then when it returns from exec, it's in this new memory space and it returns to that start address, and now we're running the new program. It turns out there's a number of different ways to do this. There's, there's some old obsolete formats. Both the Mac and the Windows each use their own format that's different from this, but does, basically the same things. This is actually the generic format that gets used for compiler output and executables. So there's a bunch of stuff in the header here, say, to be able to say, oh, this is a, .o file. It's compiler output, but it hasn't been linked to final addresses. This section contains all the symbols. This other section contains a bunch of debugger information, and so on. Obviously, exec is not going to pay any attention to those sections when it loads it into the memory map. However, your debugger is going to pay a lot of attention to them. All right. Okay, so in these, in any modern system, the memory picture created by the compiler and linker has the code being flagged as being read-only. Why? Because it doesn't make sense. Well, a couple reasons. Because it doesn't have to be writable. You know, you have your code, your C code translated to a particular set of instructions, and no matter what operations you perform in the middle of your program, it's not going to change that code that got compiled in the first place. And so it should not be changed. There's no way within the language to legally change any of the generated code, because that generated code is, reflects your original C code, which might have even been on another machine somewhere. It was compiled at a point in the past. And as I've mentioned before, if by accident you modify that code, it's really nasty to debug. Because it's one thing if your code crashes when you write to a null pointer. It's another thing if that null pointer or when you write to a bad pointer and that changes an instruction that causes a crash in a function that you don't use for another 20 minutes. So in general, for reasons of robustness and discovering errors, we would like to make these code pages read-only. This also helps us in a couple of ways. So in particular, it means that if we're low on memory, we can randomly root around in the page table, find a page in this code region that's been paged in, so it's got an allocated page, and we can evict it, which means that we're going to mark it as not being present in the page table, and we're going to free the page. And if we happen to access that page again at some time in the future, well, we'll just do the whole thing over again. We'll page it back in. No harm done, other than, it's not as fast as if we had had enough memory to keep it in RAM in the first place. Because there can't be any changes that we need to save, because it's read-only. If we had tried to write to it, we would have gotten a page fault, because it's a write to a read-only page, and then the page fault handler would have looked at this and said, "Oh, this is read-only, so this isn't. So how do I handle it? Write to a read-only page is a seg fault. Crash the program, and we're done." So that means that if we're low on memory, we can just randomly grab code pages and take them out of the page table and free them. And so this is how your laptop is able to run, multiple very large programs at the same time. If you've got Chrome and Word and Excel and a few other things, running on your machine, they are probably, between them, they probably think that they have far more memory than there is in your machine. And what the way it works is that we're only keeping the pages in memory that are actually being used. And every once in a while, the OS goes through and prunes the page table and frees up memory. And if it frees up something we actually needed, well, it's going to have to read it back from disk the next time we access it. That's also why, if you have a window that you haven't been using for a long time and you bring it back to the front, well, during all the time you were working on something else, that other program needed memory, and the OS was getting that memory in part by cannibalizing that background process. It was going through and stealing pages from it and marking them so that they would get paged back in again if they were used. And since the program was in the background and you weren't doing anything with it, it never asked for those pages back. Now, all of a sudden, you bring that program to the forefront and start doing things. Now, that's when you see the fact that a bunch of those pages were evicted, because now they have to get paged back in before you can do anything useful. But this is the basic mechanism that gets used to share what's on any of our laptops is basically quite a small amount of memory across various large programs that are using it. And then the last thing I'll talk about, well, the last thing in this section is sharing. So let's say we have two processes and they're both executing the same executable program. That's not very uncommon. Certainly in an old time-sharing machine, or if you a modern one, if you log into login.students, there's any number of processes executing the shell. Probably a fancier shell than this one, but and so each process has its own page table. As I mentioned, the operating system context switch will switch page tables from the old process to the new process. That's how we have memory protection between processes, because when you're running, your page table translates requests to your pages, and when this process is running, its page table translates requests to its pages. And that way, each process is unable to affect the other. It turns out that in some cases, it's actually safe and efficient to have pages that are pointed to by both page tables. This doesn't involve anything fancy with the MMU or anything. The MMU sees one page table at a time. We switch to this process, and it sees this mapping. We switch to this process, and it sees this mapping. So that's the whole point of the context switch, is we switch from one page table to a different one, and the MMU only sees the current one. Now, if we have a set of read-only pages, we can safely share read-only pages between two processes, because if this is a page that's supposed to be in this process and it's supposed to be in this process, it's supposed to have the same content in each of them, and we make it read-only, then each process has no idea that the page is shared with anyone else, because it's seeing the data it's supposed to see, and it has no way of affecting the other process because we can't write to it. So in particular, if we share the code pages from this executable, those pages are going to be at the same location. Those pages are mapped at the same address in each process. They're supposed to have the same content because they're swapped in from the same file. They're read-only. So we can, in fact, share those pages between these two processes. Of course, now we need a reference count and so on, because maybe this process exits, and we don't know if we can free these pages, if we have to free these pages or not, unless we had a reference count. But the key thing is that the read-only parts of a program, like the code, can be shared between multiple processes that are executing the same program. And that's not a security violation or anything, because each process sees exactly what it's supposed to see, which is, this page from this executable, and it's unable to change that page, so it can't prevent the other process from seeing exactly what it's supposed to see. So this approach of sharing code between processes worked great in, I don't know, the 80s. you've got a bunch of people logged into a mini computer. They're all running, the shell, VI, Emacs, maybe the compiler, fairly small programs, and so, you're going to be sharing pages between a bunch of copies of the shell, a bunch of copies of VI, and so on. It doesn't work so well on single user machines like our laptops, because it turns out that we're not running a huge number of copies of the same executable. We're running, I don't know, we're running a few really big processes, or a smaller number. And the thing about these processes is that a lot of their code is dominated by standard system libraries. Not for things like printf, but graphics libraries, and the menu system, the window manager, other things like that. Most of the look and feel of an application on Windows or Mac OS, or Linux for that matter, is libraries that are compiled in with your program. So your program code calls, I don't know, some GTK function, and that calls these other libraries and these others. And so a lot of this space is taken up by these system libraries. And unfortunately, if we just compile everything down to a single program, to a single code region, then we're not going to be able to share pages between these executables, because each of these libraries is going to be located at different places in the different executables. And so the code here, when it wants to open a window, is going to be calling something here. The code here is going to be calling here. It's basically none of the pages in these two executables are going to be equivalent, are going to contain the same thing, even though 80 or 90% of the code might be made up of the same libraries. So what a modern system does is it basically breaks the program up into different, let's say that Chrome doesn't have library 2 or something. It breaks this up into the core part, the core program, and then basically separate programs for each of these libraries is compiled separately, and then they're actually patched together when you exec the program. So each of these gets a place in memory, and then we patch a table in Word with the locations of those libraries, and a table in Chrome with the location. And now we're able to share code between these libraries. So this is the shared library mechanism in a modern OS, and it basically relies on splitting out these separate libraries and then into essentially separate executables. They're not standalone executables. There's no main. Instead, your window manager library has a bunch of window functions in it and stuff like that. And then we have a mechanism at startup to patch everything, to basically do the very final stage of linking the program. This has a number of advantages. One is that it lets us share memory. It means that we only need to have one copy of each of these huge libraries in memory at a time. Actually, a funny story about that was that in the very early 90s, I worked for Motorola and we were using these Digital Equipment Corp workstations, and the salespeople had basically promised whoever had purchased these that they would have shared libraries working in the next operating system release, which would let us run multiple graphical applications without running out of memory. They didn't get it working, and so I guess under the terms of the agreement, they had to give us a bunch of fairly expensive memory to make up for that. But the other advantage, so the advantage one of doing this is that it saves memory. You're able to run multiple applications using these large libraries, and that's especially an issue with, like, I don't know, I'm sure there's examples on Windows, but on a Mac, you probably have a number of apps that have those little icons on the top right of your menu bar. And each of those has to use a large system library in order to, talk to the window manager. And then the actual code that it's doing is probably a very small amount. So you're able, this way they're all sharing the same copy of the window manager library as, the others and your, more serious applications are. The other advantage is that these libraries are now separate. They're not compiled into your program. So, this happens all the time with Mac OS and Windows. You get an update to the operating system, it replaces these libraries. And so, you could have a program that you loaded on your machine 3 or 4 years ago, and when it starts up, it's going to use the latest versions of these libraries. So if they add features, if they fix a security bug, they change the color scheme, I don't know what, those changes would apply to these libraries, and then your application will pick up those changes when you start it. Last thing I'll mention is on Windows, I don't know how many people have heard the term DLL, but you know, in the Windows world, these are called dynamically linked libraries or dynamically loaded. They're called DLLs. And they've used them for a long time and sometimes problematically. All right, so I think I'm going to finish up and ask for questions on the material I covered. Who has? Yes.
With the shared libraries, is the exec programming that's like piloting and allocating like addresses for them? Is it only doing it for like the libraries that have circles around them?
It's complicated. There's something in here saying which external libraries it depends on. And then, in fact, exec doesn't do this. There's something else here that says that the kernel shouldn't actually execute this directly. It should instead execute this interpreter, which is going to go and figure all this stuff. You know, there's an external program which does the work of patching together all the libraries, and there's a database so that there's an optimized database so it can hopefully do it quickly. And there's a whole bunch of stuff there that you know, that we don't need to learn in this class, but it's, you know, actually what you can do though on your virtual machine is in Linux is I'm not sure what LDD stands for, but this will display all the libraries that that a file uses. So, you know, when you compile your file for this class, it probably has like 3 or 4 libraries it depends on. If you look at a graphical application, there's probably 30 or something. Other questions? All right, so just to go back over, page faulting. So if a memory access is not allowed by the page table, it's not present, or it's a write to read only, the hardware will invoke the page fault handler. The neat thing about a page fault is that when it returns back, it's going to retry that instruction. The operating system, we talked about 3 possible. The operating system is going to have its picture of what the address space is supposed to be. That's pretty much based on information from this header. You know, in the case of here, it'll include all the libraries that got added into the address space as well. The page fault handler looks at that list of mapped regions and finds the one where the fault occurred and decides what to do. If it doesn't find anything, it crashes your program. If it finds a demand allocate page, then it allocates memory, wires it into the page table, and returns. And so your program never finds out that the OS promised to allocate memory, but it didn't, because by the time you finish the instruction accessing that page, it's been allocated. There's demand load, which gets used, primarily with executables, the programs and libraries, and there, that entry says that it's loaded from a particular file. And that's the end of the lecture, and I will